So the last topic before the test is some coverage on lipids and biological membranes. All right, so lipids is one of our four major molecules that we have to be concerned with in biochemistry. What were the other three types of, so lipids, what were the other three categories of biomolecules? Protein is the polymer, amino acid, nucleic acid, carbs. Yes. So of those four, lipids, amino acids, nucleic acids, carbs, three of those four can polymerize. Is lipids one of the choices that can polymerize? No. Which makes it able to do a whole bunch of other chemistry that the other three cannot do. All right, so lipids do not polymerize. They aggregate. What does it mean to aggregate? Using some hand symbols. Yes, they kind of do this, they clump. It means that they choose to associate with themselves rather than other molecules. It's one of those likes statements. So their job is to serve as structure-bearing units. And as such, they can exhibit a variety of structures as a structure-bearing unit. And most often, the structure they're going to be found in is called a lipid bilayer. Which in the body is going to be your cell membrane. Good. Okay. So let's talk about all the different classifications that lipids can fall into. The first, and the one you're probably most familiar with, is something called fatty acids. Fatty acids can have three different structures, which you probably use in your food terminology all the time. You probably just don't know exactly what it's referring to. You have your saturated fatty acids, your unsaturated fatty acids, and your polyunsaturated fatty acids. So a fatty acid tells you that is a carboxylic acid on one end and a long chain of hydrocarbons on the other end. So here are my four options of fatty acids. I have stearic, oleic, linoic, and alpha linoic. They all have a carboxylic acid head. And they all have a long chain of hydrocarbons. What end is the polar end? The red head or the blue tail? Yep, that's your polar end. These long chains of hydrocarbons is going to be nonpolar. Let me give some general information about fatty acids, and then I'll talk specifically about three subcategories. So in general, Fatty acids have a long tail between C16 and C18. That's a better sentence. So C16 to C18, so there's between 16 to 18 carbons in my non-polar end. Fatty acid tails only come in even number units. Because of the way they're synthesized, which if you're taking Biochem 2, we spent a whole unit talking about fatty acid synthesis, but if you're not, just a fun fact. Fatty acid tails only come in even number of units. All right, since my picture's real big, I'm gonna write on another sheet of paper here. All right, so let's talk about my saturated fatty acids. When I'm talking saturated, what am I telling you about the structure of the long tail? It has no double bonds. It is all single bonds between my CH2 units. So saturated is another way of saying fully reduced. Means there's no double bonds. They're all reduced to a single bond. So of my 4 options up here, which one of them is the saturated fatty acid? Yep, this guy over here, stearic acid. Saturated fatty acids are also very flexible because they don't have any constraints they have no double bonds, so no constraints there. And as such, they are able to pack tightly together. You can imagine a whole bunch of them line up real nicely together. All right, so then let's compare that to an unsaturated fatty acid. And as the name implies, this contains at least one double bond. Now, knowing what we know about double bonds, what is the preferred conformation of most things in a double bond? Cis or trans? Most of the time, it's going to be trans. Let's look at our picture of our fatty acid here at C9. What is the conformation it is showing there? Cis or trans? It's showing cis. Fatty acids almost always have their double bond in the cis conformation. And there's a reason for that. Oh yeah, question. It does. It does that because they do not want to pack super tightly. There's times when you want your fatty acids to have some flexibility in between them, so maybe you could stick a protein in between them. And so if they were all trans, it would like lock together. And by having some cis sticking out, it provides some flexibility in the packing. So, I enjoy this unit because it lets me talk about food. I'm real passionate about food. So, when you are listening to the commercials on TV, and they are telling you that it's zero trans fat, right? They are talking about this. And so trans fat is man-made. Fat normally comes cis, so it's normally cis fat. So when it says zero trans fat, it means they have not chemically modified the fatty acids to force it into the opposite conformation. So margarine, for example, is all trans fats. It is artificially made fat. They've taken regular fat, chemically modified it, so that it is in the opposite conformation, because your body doesn't know what to do with it.
Yeah.
So it passes right through. Like, we'll talk about Olean a little bit later. I don't know if everybody remembers Olean. The ridiculous fake fat that gave everybody the runs. We'll talk about that a little bit later in this chapter. But Olean was real popular because the idea was it was a fat that made your chips taste reasonably normal, but your body didn't know what to do with it, so you pooped it all out, like violently pooped it all out. And so they took that off the market. But when they're talking about no trans fat, they are saying that all the fats are in the cis conformation, so your body should be able to process it fairly reasonably. So, there you go. There's your fun fact for today.
Is it fat? It's always cis.
Should always be cis, but it's not very sexy to say no cis fat, like, or all cis fat. Nobody would know what that means. Like zero trans fat indicates somehow that trans fats are worse, which they're not necessarily worse. They're just different. Your body just doesn't know what to do with them.
Yeah.
And so if they say 100% cis fat, you guys in this room would be like, oh, cis, I'm on it. Everyone else would be like, I don't know, is that better? I don't know if that's better. So, hopefully by the end of this class, if nothing else, you'll be better food consumers as to your fats and carbs. All right, so that's saturated, unsaturated. Let's also talk about our poly. So oleic is an example of an unsaturated fatty acid, which is where the idea of Olean came from, where they messed around with oleic acid to make it Olean, which is the trademark name. And so I'll talk about that later, about what happens when you digest your fatty acids. I'm a big proponent of colon health, so we'll be talking quite a bit about your intestinal tract later, and good things and bad things that can go on down there. So. Polyunsaturated. Again, the name's kind of a giveaway. It has more than one double bond. Now, for a polyunsaturated fat, because of the way the fatty acids are made, the double bond can come no earlier in your chain than C9, which is why they're showing that in the figure. C9 is the first place you can have a double bond. It comes from the way that they're made, that this is the first option available. So double bond starting at C9. In a polyunsaturated, you can't have double bonds between all the bonds. You can only have double bonds between every third carbon. So they're added in lengths of 2. So in this case, 1 and 2 were put together, then 3, 4, 5, 6, 7, 8, 9, 10 were stuck on together. That was reduced to a double bond. 11, 12 was stuck on. You can't put that as a double bond. You gotta wait till 12, 13. Just the way it's made. So it contains at least 2 double bonds. The first of which And that occurs every third carbon subsequently. What would happen if it was, oh, yeah.
Will it always occur like every third carbon, or will it only be like maybe 2 double bonds?
It may just be 2 double bonds. So like in this, the linoleic acid is just 2 double bonds. This alpha linoleic acid is 3 double bonds. What would it be if it was every other carbon? What would I call that kind of molecule? Every other carbon was a double bond. Conjugated. These cannot be conjugated because it's every third carbon. So that's another thing. They don't want to be conjugated. They want to be specifically unconjugated. Questions on our categories of fatty acids? Oh, yeah, sorry. Cannot be conjugated. Oh,
Could there be more than 3 carbons between them if it's a multiple of 3? Like 6 carbons between 2 double bonds?
theoretically, yes. I'm not totally sure it actually works out that way, but it could be. Yeah. Okay, let's talk about another category of lipids then. Oh, before I forget, so there's this table that talks about common biological fatty acids and their melting points. So what they're showing here is 12 carbons in the long chain, 0 of which are double bonded, 14 no double bonds, 16 no double bonds. Down here we have 16 carbons, a double bond, number of carbon atoms, number of double bonds, the position of the last double bond. So that's the one we just looked at, 18 in the first double bonds, it's 9, 8, linoleic acid, this one we just looked at. So their numbering system's kind of funky. You just need to know that as you move down, there's more double bonds. Yeah, 1, 2, 3, 4. All right, the thing to point out, if we look at our saturated fatty acids and the melting point, as I have more carbons in my saturated fatty acid, what happens to my melting point? It increases, right? More carbons, higher melting point. That comes from the fact that these guys, no double bonds, tightly packed, requires more energy to melt. All right? No double bonds, tight packed, more energy to melt. What would you say? So I guess looking at these, are these fats liquids or solids at room temperature? These are all solids. So typically, a saturated fatty acid will be one of your saturated, like solid fats, like Crisco. That's an excellent example. Crisco is a, or lard.
Say that again, the ones that are at room temperature are
Solids. Right, so all of our saturated don't melt until way above room temperature, so all of our saturated fats should be solids. Looking at my unsaturated fatty acids, where all the double bonds are in the cis conformation, are those typically solids or liquids? Definitely liquids, right? If this is melting at minus 17 degrees Celsius, that is definitely a liquid at room temperature. So unsaturated fatty acids do not pack as well, therefore they are typically a liquid at room temperature. Yeah.
the trans fats being solids.
Yeah. Trans fats can be a solid, which is why they're sold as usually your margarine or your artificial butter, because they're a solid that's spreadable, but then kind of melts, sort of. But you can't use it in cooking because it doesn't have the same chemistry, which we will get to. Why you can't substitute margarine for butter as easily. Yeah, Katie.
So in like the polyunsaturated, you can't have double bonds with C9.
Yes.
But in unsaturated, do you have a double bond before C9?
Potentially. Yeah. Yeah. All right. I'm a big fan of food chemistry. Just a big fan. Alton Brown, personal hero. Love that guy. I'm actually teaching a freshman colloquium next fall called Chemistry of Food. So, yeah. So, no, not at all. I find it's more important to do my research by eating a variety of terrible foods. Otherwise, I can't articulate how amazing a deep fried cheesecake ball is, right? Have you not been to the fair? Oh my gosh. They take little pieces of cheesecake and then they roll them in batter and then they deep fry them on a stick. Or fried pickles on a stick, that's good too. A dill pickle roll. Or hot dish on, when I was in the Minnesota State Fair, hot dish on a stick is a meatball, 2 tater tots, and then they roll that in batter, deep fry it, and then serve it with a side of gravy. So you can like. Oh. It is amazing. Pretty much if the food is able to be served on a stick, I'm sold. I want to be able to walk and eat at the same time, so on a stick. So the answer is no, not particularly healthy either. I'm working on it.
So what's your snack after this class?
I have lunch actually after this class because I teach again at noon. So yeah, you don't want to know what I brought for lunch. Not great, not a great choice. It's chicken and dumplings. That's not terrible, right? Right? A lot better than a lot of the other things I could be eating. So. All right, so triglycerides are another option of fatty acids. These are typically nonpolar. Which would mean that they are water insoluble. So do I have this on 2 pages? I do. And what these are fatty acid esters of glycerol. So glycerol is this molecule down here. It's 3 carbons, each of which have an alcohol on them. And for the fatty acid ester, I have now made this alcohol group into this ester group. So glycerol is now converted to a triacyl glycerol, saying that glycerol is still the base molecule, but now I have an ester. So here is an example. It is 3 fatty acids. We just looked at palmitoyl, we looked at linoleic acid, and we looked at stearic acid. So those are 3 fatty acids that have now been hung off the end of my triacyl glycerol. So 3 fatty acids. They can be the same, they can be 3 different. Either way it works. 3 fatty acids. So here's my glycerol, my ester form of it. This is saying that's 1 palmitoylic acid. That'd be this one. And it's saying the number 2 is linoleic acid. That's this one. And then it's saying this one's stearic acid, which it is. So in the naming process, 3 fatty acids, and it's telling you which order, reading left to right, they're stuck on there. 1, 2. So, why do we need triglycerides in our food system? We use them as our energy reserves. This is how you store energy in your system. There's a way to store fatty acids for a release of energy later. The reason we store fatty acids is that it takes less energy to oxidize them back into energy usable forms than it does for carbs, which is why your body stores fat. It doesn't store carbs. It can convert carbs to fat, but your body cannot store carbs. It stores it as fat for use later or when it's cold. either way. If you're a whale or something in the ocean. In the ocean, swimming around, you need to store your fat reserves for warmth.
So it takes less energy to store the oxidized.
It takes less energy to convert fatty acids into this form, and it takes less energy to convert them back out.
Okay.
Yep. It's a low energy storage way. So for those who are more familiar with biological terms, this is your where we store these is our, we have our adipocytes. I've never actually heard it said before, so that word? That's where you store your fat. Specifically, you store your triglycerides in those specialized cells. So for animals, these triglycerides typically contain 3 different fatty acids. Just like in the picture we just looked at of a triglycerol, the 3 fatty acids that were being linked together are 3 different ones. Fatty acids cannot form bilayers. I'll write that here. They instead form the technical term globules, globs, they glob together. So we can use fatty acids to form membranes, but not in this form. This is the energy storage form of fatty acids. So fatty acids can be used to form membranes, but not if they're in this form. Questions about my triglycerides? Okay. Another form of lipids is glycerophospholipids. This is the predominant way that lipids are used to form biological membranes. So, based on the fact that it's called glycerophospholipids, what are 2 components probably attached to the lipid? Glycerol and a phosphate group. Excellent. So hopefully that helps put it all together. So a glycerophospholipid contains this right here, glycerol 3-phosphate, which we see right here. That's my glycerol 3-phosphate. And then it contains 3 fatty acids. One of which, I guess we're showing them down here. One's here, sterol phosphatidylcholine. So 1, 2, and then there's this X group. So sterol is this one, that's that one, phosphatidylcholine is up here. So its name, the name tells you which ones they're stuck off of, right? Number 1 carbon is a sterol fatty acid. Number 2 is an allesyl fatty acid. And a third group, which they call X, could be a fatty acid or it could be a different functional group. And in this case, it has a choline function to it. Because it should have a polar and nonpolar end. Is the polar end pointing towards the top of the page or towards the bottom of the page? Top. So the polar, in this case, is this end with that NH+. My nonpolar end is down here. why would it be important for a glycerol phospholipid, if it forms biological membranes, to have a polar and nonpolar end? You need to have a hydrophilic, hydrophobic part. What is your cell floating around in? Water. So you need to have it so that my red are all on the outside of my cell. You have your little black tails pointing in. Then, what liquid's on the inside of your cell? Water again, so you gotta have your tails pointing back out with a bunch more of these. Good, good. So I have to have a polar and nonpolar end. I can line it that way. Questions on my glycerophospholipids? Okay. Another word I'm not great at saying. Animal science folks will have to help me out. I got my sphingolipids. Sphingo, is that right? Okay. It is another component of the membrane. But it's not the majority item that forms the membrane. It is a component, but it's not the entirety of a membrane. All right, so sphingosine is a fatty acid that is a derivative of a C18. So what's the 18 referring to? Number of carbons off the bottom. So it's a derivative of a C18 amino acid, sphingosine, who has a trans double bond. So this is an odd fatty acid in that it has a double bond in the trans conformation. This fatty acid. So you can see, here's the amino acid sphingosine with our 12, 13, 14, 15. So our 18 carbons hanging off the bottom. The fatty acid that turns into is a ceramide, and we've changed our amine group to this amide functionality. When we do that, one of the things we can make is something called ganglioside. And the reason we care about gangliosides is that it is the majority membrane component of your brain membrane. It is the fatty acid that makes up the largest portion of your brain membrane. So ganglioside is made up of a few things. So this over here is ganglioside. Here is the sphingosine, which we just looked at, which is that fatty acid. It also has stearic acid, which is the other fatty acid. And then we haven't gotten to sugars yet, but it has a bunch of sugars attached to it. The reason I picked this sphingolipid out of all the sphingolipids that there are possibly out there is that this, when there's a malfunction in the ganglioside development, you end up with a disease called Tay-Sachs disease. I don't know if anyone's familiar with Tay-Sachs disease. Tay-Sachs disease leads to a deterioration of mental and physical abilities. Not metal. And typically a Tay-Sachs disease patient only lives to the age of 4 because their brain membrane has not fully developed. Like there's an issue with it. And so age 4 is the maximum life expectancy for a taste-X disease patient.
Hereditary?
It can be. It's one of those ones where obviously one of the parents would have to have the recessive gene. If you have 2 recessive gene parents, then they're likely to get this. Okay. Another great class would be talking about steroids, but I'm not going to do that all today. So steroids are derivative of fused planar rings. So they fall into the category of fatty acids, but looking at, I guess any of them, looking at any of them, do they look like all the other fatty acids that we've looked at? No. 1, they're not long chain, they're fused rings. 2, do they have a distinct polar and nonpolar end? Not really. So cholesterol falls in this category of lipids and fatty acids, but physically they do not have the same characteristics. The main reason we include them is that they are critically important to your membranes. And just like all of our fatty acids are typically in the cis position to keep them from packing very tightly, same thing with these cholesterol derivatives. They will be in the membrane, in the non-polar region, making some space. They're going to push apart the fatty acids to leave some room to do some other chemistry. Keep them from packing very tightly. So you're probably familiar with some of these. Cortisol or hydrocortisone, which is an anti-inflammatory. Testosterone or estradiol, which is an estrogen compound. Right, men, women. And then there's just another version, an aldosterone, which is a corticoid steroid. Yeah, what did I say? I guess yeah. So we'll talk more about these guys later, but just getting through kind of the 4 big categories, five big categories. Okay, a caveat to the steroids and the fatty acids are fat-soluble vitamins. There are 3 categories of fat-soluble vitamins, A, E, and K. So, I'll start with vitamin A first. Here I just put my notes up. There we go. All right, anyone know where you can get vitamin A in your diet? Carrots is a good choice. Dark leafy greens, always a good choice. Actually, I'm going to write this on a separate page so I didn't leave myself any space. Okay, so 2 good examples of vitamin A. Carrots, dark leafy greens, pretty much any food that's orange. So you got your sweet potatoes, your pumpkins, and your squash. All of those orange foods. So what did your family always tell you about eating carrots? Why do you need to eat carrots? For your eyesight. So retinol is the major component, once it's esterified, in your rods and cones in your eyeballs. You can see why it's called retinol, because the major component in your retina. That helps you put it together. You also need it, so for anyone who's ever taken any acne medication, vitamin A is the main component of all those because it encourages your immature skin cells to become mature skin cells and hopefully replace the older, not so great skin cells. So all those oil of Olay commercials where they're putting the stuff underneath their eyeballs with retinol A and whatnot, they're just using vitamin A to improve your skin health. All right, for all of these vitamins, obviously these are the why you need. Another interesting fact is what happens when you don't get them. Deficiencies. That's a good one, night blindness. As a starter, like if you notice night blindness, you're possibly on the path to some bigger issues. Turns out that about a third of the children of the world population are currently vitamin A deficient. About a third of the children under the age of 5 are vitamin A deficient. Probably about 500,000 children each year go blind because they didn't get enough vitamin A in their diet. Obviously, there's going to be pockets of the world where this is more prevalent. Parts of the world that don't eat a lot of dark leafy greens, sweet potatoes, squash, whatnot. It's probably more Asia than anywhere else. Let's see. Yeah. All right. The other half of this is like, fine, you can be deficient, you can make that up in your diet. There's the other extreme, which is toxicity. So your fat-soluble vitamins, your A, E, and K, are the 3 vitamins that you don't really need supplements for because your body stores it, and you can, in fact, overdose on all 3 of those vitamins. So, in theory, you could, actually, it's a fun story. When I was probably 1.5, 2, I would only eat orange foods. Remember, I went through a phase. Went through an orange food phase, and I turned, like my skin turned orange because my body was storing so much of the vitamin A. My skin turned orange that you had to actually cut back on how much. Yours turned orange? Yeah, so probably. I have to ask my parents for one. But, I mean, it wasn't like bright orange, like neon orange. It was just like a shade of orange. So you can't. Yeah, kind of like a spray tan, where you're like, there's just something funky with that. So it turns out you can overdose on all these fat-soluble vitamins. So toxicity for vitamin A occurs, you would have to eat around you'd have to eat around 200% of the daily dose for obviously a few days, quite a while. Which 200% of the daily dose is not an unreasonable amount if you think about it, because really 1 serving of sweet potato is about 100% of your daily dose. So if you start eating like 2 sweet potatoes every day for days and days and days, which is what I was doing. Right, and that's what it is, like depending on the size. A typical sweet potato, American gigantic sweet potato, is really 2 sweet potatoes. So it doesn't take very long to go crazy with it. All right, I will save the rest of the fun facts about fat-soluble vitamins. Let me double check. There's going to be one. No, I think just today. Yeah.